Hello everyone, welcome to Statistical Foundation for Big Data Analysis. We will continue with our first module on statistical learning theory. This is the fourth lecture. We continue our discussion on bias, variance and mean squared error. Let's start from scratch once more, the formal setup. So you are drawing a data set x1, y1, x2, y2, x and yn independently from some joint distribution of x and y. Here potentially x can be multiple featured, y we take to be single featured, that is x of x, we take x to be potentially a vector and y we for now take a scalar, and the goal is to find a function or rule hs in order to model y in terms of this sample data s. So you come up with this hs based on this sample. So your modeling will be something like this. Once you find hs, you potentially can discard the sample and apply this this function, this rule on any x to predict y. So the goal is to use this sample, come up with a prediction rule for y based on x. Of course, this prediction rule you are creating it out of the sample. You have no way to see whole of the distribution. Remember, distribution underlying population is totality of all possible measurements, which is by nature because it's unknowable. Sample is just the measurements you can observe. Based on that, we are coming up with this rule. So this rule potentially can be a simple rule like just a line join, the least square, the best possible line that fits this data point. It can just be some other simple function, or it can simply be an algorithm also. It can be an algorithm fit through something called neural network, which is nowadays one of the most highly valued algorithm that is used in machine learning, big data, etc. And now the point here in this learning theory is to realize that hs is also a random variable, strictly speaking, because this data itself, these x1, y1, x2, y2, x and yn, they are being drawn from the population. The sample itself can be anything from that population. The purpose of this study is to actually not stop at finding hs. We will see that in case of linear regression, we will do linear regression carefully in some future module, where we will see we make the assumption that there is some linear function that describes y well in terms of x. Under that assumption that there exists something, we come up with the best possible thing. Here we are making no such assumption about the distribution. Distribution can be anything. You happen to have a sample. Based on that, you have come up with a rule. How good that rule is? I mean, we were giving you some example, like one can do something like if your sample points are like this, even in 2 dimension, you can simply get a rule which is like this, which will explain the sample you got perfectly. I mean, one can make it even worse. One can, this is clearly the relation has a linear kind of thing. You can always find a very ugly function which nevertheless fits the sample perfectly. But obviously those kind of functions, although they will explain the sample well, are not potentially pretty bad estimators. You can almost see it from there. And in this module in statistical learning theory, we precisely want to judge whether your estimator is like that, or it has some other flaw, or is actually a good estimator. So for that, we need to consider the sample as a random variable. It's really important to visualize sample as a random variable and compare hs and study how hs, once that you have the rule which if you feed the sample in that rule, it is giving you an hs. It's important to understand for various different samples how these rules behave. So we started with discussing this thing. First of all, because probability distribution can be discrete, absolutely continuous, it can actually be something neither discrete nor absolutely continuous. For now, we are not concentrating too much on like most abstract probability distribution. One, we are thinking either it is discrete or absolutely continuous, and we more or less always use this in this module at least notation integral to mean either integral or sum. Integral is also kind of an infinite sum anyway, and this integral for some function L z1 z2 L z1 z2, let's say probability z1 given z2 dz1, this essentially means expected value of z1 with respect to the conditional distribution keeping z2 fixed. So, this will essentially indicate which we will just use this PR to simply note the probability distribution you are using to calculate the integral. So, not expected value of z1, but expected value of L with respect to the distribution of z1 given z2. This is what we will mean. So, here we defined this earlier, but just to quickly have all of it under same roof. So, y bar x is the expected value of y given x. So, for a fixed value x, you take, so you know it's a joint distribution of x, y, you take for a fixed x, what are the values y can take their average, that is y bar x. Expected test error for a given sample. So, if your S is fixed, based on S, you predict what y is in terms of x. So, for fixed, so S is fixed, this rule Hx is fixed. Once this is fixed, for every x, you can predict y by Hsx, but then there is actual value of y. You take their you take their difference and take the sum, the squared difference between predicted y and actual y, and then take average over the whole population. That is the expected test error. Now, there is an important qualification here. This is for a given sample. Here the rule is fixed, you are only varying x and y. You are not taking rules over various samples, because there is one extra parameter that will be involved, like there is one extra random layer of randomness one has to consider after this, namely if one varies the rule. So, that will be the total error, like you take for all possible s, all possible x, all possible y, the difference between Hsx and y, take their square and then take average over all possible x, y, s, then that will be the grand error. We will get into that, but this is the expected error for a given sample. For a given sample, you have a fixed rule. For this rule, what is the average error over all the population when you predict y in terms of x? And expected value of the predictor, well, expected value of the predictor means basically, so you are taking, so now expected value of the predictor essentially means this: you take, for a fixed x, so h bar, basically h bar x is, you take expected value of Hs with respect to x, Hs with respect to you take expected value of Hsx by moving s, that is you take, so here x becomes the one which you are viewing h bar as a function with respect to. So, you take Hsx, so maybe not right here. So, this is basically integral of hs x, and then you do it with respect to probability distribution of s. So this is here x fixed. So for a fixed x, you take the predictions for y for various sample and take the average of those values. Average is taken over all samples. So this is your h bar. So this is expectation is taken over all is hs x. This is your h bar. So that is the expected value of the predictor. So that it's the expected value of the rule. It's the expected value of the algorithm. So the and what is the expected value? When you take an average sample, what is the predicted value for y for a given x? Now the bias, we define bias is the average predicted value. For bias of a prediction is that you take x, a value for x, take the average predicted value h bar x. So basically you take a average sample and take the predicted value for y for that average sample, and take actually the average value for y when your x value is the given value, and take their difference, their squared difference, and take the sum over all x. So this is your population, this is your x, this is your y. So here is somewhere y bar x. Now suppose the rules are like this. So let me explain. So suppose your population is like this. This is your x. This is the average value for y. Now suppose rules are like this. This is one rule. This is another rule. This is another rule. This is another rule. So these are the expected value, these are the predictions for those rules. Now if you take the average of these things, the average comes here. Now you will take the difference, squared difference between these two. Now if you vary x, you come x here, the expected value for y for this x is probably here, and the averages are of these values will be somewhere here. You take the squared difference between these two. You keep doing this. So these are hs1, hs2, hs3, hs4. For various potential samples, these are the predictions, prediction lines. Now for this x, you get these prediction values and you can take the average over the samples. Suppose this comes out to be this. And also for this x, you have this population. So suppose this is your predicted value for y, the average value for y when x is this. Now take the difference between these two averages, take the squared difference. For this x also do the same, this is the squared difference. Take this out. Now take the average over all the x's of this squared differences. That is called the bias. So tentatively speaking, the difference between the predicted y, average predicted y, is the average of all the predicted y's. So for each sample you will get a prediction for y, take the average of that. So for one sample the prediction may be somewhat awkward, but if the rule is good, the expectation is that average of all these predictions should give you a correct, correct direction. Now this difference is the bias for this particular x. And now if you do this over all x's, that gives you this grand bias. So just to give you a real life analogy, before every election you will see that there is exit poll. Okay, each exit poll does, assuming the exit polls are more or less following similar technology, similar sampling technology and sample to sample to population prediction technology. each exit poll does it for a particular sample. So it is giving you some rule. Based on that, you are predicting something, some results for various parties. Now, if you after the various agencies will do exit poll, TV channels will do poll of polls. So the understanding is that people try to say that even if the various agencies give you somewhat different results, generally poll of poll tends to predict the election well. That's the general understanding. Now, the difference between the actual result and the result of poll of polls, the average of all the sample polls, gives you the bias. And in some cases, some elections, you will see that all the exit polls are showing a particular direction and the result is somewhat off from there. So then the result of poll and the difference between result of poll of poll and the result of the election is the bias. That actually shows you maybe the thought leaders, think tanks, missed something on ground. So that is literally the bias. What is there? This algorithm is missing that. So this is the bias of that algorithm. The average, one particular sample may give you a particular result, but the average should give you close to the actual. If it seems like there is a difference between the average of these, all the samples, the rules that comes out from the average of all this and the original, that's called the bias. So that bias is something inherent to the construction process of H. So that's the algorithm that is giving you to H. This bias is a lacuna in that construction process. That is so there is something in the construction process that is missing a certain feature of the underlying distribution. For example, we talked if the distribution is something quadratic or something complex, if you are giving a linear predictor, that will miss the quadratic structure or the high dimensional complex structure, and then it will end up giving some high bias. So that's what we are saying. That's what it is doing. This shows you the algorithm is missing something about the distribution. Now the alter ego of the bias is variance. Variance says something interesting. Variance says for each x and each s. So suppose this is x. For S1, suppose this is your predicted line. Suppose S2, this is your predicted line. S3, this is your predicted line. For each S, let's say average of all these predictions for S is somewhere here. Now there will be a difference between prediction for S1 and this average prediction, S2 and this average prediction, and S3 and this average prediction. You take the sum of squares of them and take the average of these predictions and take the average over, first of all take the average over all these all these samples, and then take the average over all x's. What that gives you is the variance. So this actually tells you how closely knit, how robust the algorithm is. Like, you take any random sample, that should give you more or less similar prediction. So this is essentially, if you go back to the very old population central tendency and dispersion thing, it essentially says whatever the mean is. But by the way, this does not say, I mean, the actual population can be here and you can predict something here. You can make a prediction rule if this is your population and your prediction rule is just constant y equal to, let's say, minus 100 for all sample. If this is for all s, then this will have very low variance, because for all s, for all x or whatever, minus this will be, y will be minus 100. So in fact, particular for all x, this will be minus 100, this will be minus 100. So their difference will be 0. So the variance will be 0. So variance law doesn't mean necessarily it's a good predictor, but variance law means it's for different samples, it gives you close prediction. It gives you, there is not much difference between the predictions constructed from different samples. And finally, the grand error we were talking about, this is the predicted value for a particular x and particular x. So, if you have a xy and for a particular, if you have take a population point xy for a particular sample S, this is the predicted value for y and this is the actual value for y. You take the squared difference, you integrate over whole population and all possible sample. This is the grand error. So, basically this is the complete total error for the prediction rule. You take all possible sample and all possible population point. For all possible samples and all possible population point, you take the difference, square difference between predicted value and actual value, and then sum it over, take average over all possible population point as well as all possible sample. That expected value is called the expected test error. We may as well say it expected grand test error. We can even say grand test error because it's taking care of all possible randomness involved in this problem. Takes care of all possible randomness. Takes care of all layers of randomness. So, now we move on to the calculation. We just give you some example. I mean, for today's class, my goal is just to understand these things very well. So, suppose suppose your true function, actual function y is actually follows, y is indeed 2x. Suppose that is a true function. Suppose x is the distribution, it takes value 0 and 1 with probability 0.5. So, the model prediction, and suppose model always predicts y hat to be 1. So, let us say this is a artificial scenario, but let us say that is the that is what it is happening. So, since model always predicts 1 for all x, the average prediction will always be 1, but expected value of y is 2x because y is actually 2x. So, expected value of y given x will be 2x. So, bias will be this predicted value minus the average actual expected value of y. So, and then its expectation over x. Now, x can take value 0 and 1. If x is 0, it does not matter, hx is 1 because it is always 1, but y bar will be 0. This is square times probability half. So, this is basically h bar 0 minus y bar 0 times half, because that is the probability for that, times h bar 1 minus y bar 1 times half. Now, this is 1 times half plus 1 times half, half. So, this is the bias of this model. Of course, this is a very artificially constructed model, just to explain what these values are. The same thing, suppose 2 training sets gives you prediction HS1 to be 0.1, that is training set means, this is a term generally means sample. Suppose you are getting the same scenario, you are getting prediction 0.8 and 1.2. So, here the mean prediction for every x. So, now this is 2 samples, let us say you are drawing S1. So, suppose I assume S1 and S2 has probability half each. I mean only 2 possible sample with equal likelihood. So, the expected value, the mean prediction will be what? For every, for every x, this is 0.8 and this is 1.2, so it will be 0.8 times half plus 1.2 times half, so it will be 2 times half, it will be half. So the variance, what will be the variance now? The variance will be hsx minus h bar x whole square, and you will take expectation over all s and all x. So now we'll come to s later. So let's see what it happens. So we'll take the average over s later. Let's first take x fixing something given to you. Actually no, the reverse way. So we'll come to different x's later. See, basically it doesn't change with various x's. So the way we have chosen, so we'll take x later. So let's do it for all s given x. hs x minus h bar x whole square. Let's try to do this first. But now here there are only two samples with each with probability 0.8. So it will be 0.8 minus, the prediction is 0.8, h bar is always 1, so 0.8 times 1, and the probability of this sample is half plus 1.2 minus 1, and the probability is half. This will actually give you 0.04 plus 0.04, which is times half, so it will be 0.04, so it will be expected value over x of 0.04. The thing is, expected value of over x doesn't matter because you know it's free of x. So only thing matters is basically equal to expected value of over s of this. That's it. So this is the calculation for variance. So two possible sample, each has probability 2, each probability half, equally likely. So now next example, here we are making it slightly more complicated. Suppose y is 2x plus 1 plus epsilon, where x takes uniform 0, 1, 2 values, that is each probability x equal to I equal to 1/3, where I equal to 0, 1, 2, and y follows this distribution. Y is 2x plus 1 plus epsilon, where epsilon is normal 0 sigma square. Now suppose you have potentially three samples, each with probability of xi, yi, let's say, is 1/3 for all, 1, 2, 3. Suppose you have 3 training samples. Now here you are getting this data where x0 is 1, x1 is 1, x0 is 0, x1 is 1, x2 is 2, and you are getting corresponding y's. Whatever the corresponding y value is, if it is not 2xi plus 1, the remainder part, like yi minus 2xi plus 1, from this it is clear that it is epsilon I which follows this distribution. So now when we are getting into the modeling business, you are given 3 data point and you have this information. Suppose you fit a straight line. If you fit a straight line such that which follows the least square criterion. Suppose which fits the least square criterion in this data. You recall that in one class earlier we actually discussed this least square fitting, where for a fixed data this becomes basically a function of a and b. So you just it's a 2 variable function. So you find the partial derivatives and put it to 0 and find the critical point, and taking the Hessian you can actually show that that's a minimum. So you can find the minimum, you can find the minimum value for this. Now, this is the least square curve. You can actually, we discussed this earlier. I also have, just for the sake of completion, put it in the notes. This is what it becomes. So, now if you put it in these values and do the simplification, this will be your fit. This will become the predictions. So, since yi is 2xi plus 1 plus epsilon I, and you can put this in this AS, because AS and BS both are found in terms of yi's, you can rewrite them in terms of, because this is y1, y2, y0 is there, and values of x's are given to you, values of x's are given to you, you can compute the corresponding values for AS in terms of these epsilons. Okay. Now, from there also you can calculate the values of B's. So, you have a value for AS in terms of epsilon here, value for B in terms of epsilon here. So, this becomes your summary of estimate. Now, when you are taking potentially expectation over all samples, when you are taking expected value over all sample, so this becomes expected value of this thing over all sample. Now, expected value of 2 is 2, expected, and all these epsilons have expected value 0. So, this becomes expected value of this thing becomes 0. So, expected value of AS becomes 2. And similarly, expected value of BS also, because all these epsilons have expected value 0 and this is a linear combination, expected value of B becomes 1. So, your predictor HSX, predictor H bar x is the expected value of this HSX, which is basically expected value of AX and expected value of BX. This becomes 2x plus 1 for a particular x. For a particular fixed x, this becomes 2x plus 1. So, this becomes, now if you want to calculate the bias computation, expected value of this is 2x plus 1, expected value of y bar is 2x plus 1. When you take the difference, the bias becomes 0. And similarly, you can get into the computation of variance. HSX is this and H bar x is this. It takes the difference between HSX and H bar x. This becomes basically this times x plus this times this minus 2x. Now, you have this expression. So, if you are these things, because you are taking IID sample and this is equal to this, when you calculate the variance, you actually get the sum of these squares and this gives you variance to be x square minus 2x plus 5 over 3. So, now when you are taking average over all the x's, that variance comes out to be 2 sigma square over 3. So, finally, from here you can calculate the expected whole test of error. When you are taking all of it, this is your prediction, this is your y, HS minus this becomes this. When you are taking expected value of I is 0, variance this is sigma square, the expectation of this is this. So, now you are taking over, see this becomes basically you can, these variances are 0 and this is sigma I squared. When you are taking the expected value of this square, you utilize this formula you derived earlier and it becomes this expression, and now you average over x's, you get the total error to be this. Please take a close look at this calculation at your piece. This is for a very specific small example, but it is important to understand how these bias and variances are calculated for specific example. I stop my talk here. Thank you.